Welcome to the Industrial IoT Spotlight, your number one spot for insight from industrial IoT thought leaders who are transforming businesses today. With your host, Eric Walenza.
Welcome back to the Industrial IoT Spotlight podcast. I'm your host, Eric Walenza, CEO of IoT1, the consultancy that helps companies create value from data to accelerate growth. And our guest today is Dave Fick, co-founder and CEO of Mythic. Mythic has developed analog computing technology to deliver high-performance AI processors that are 10 times more power efficient and cost-effective than digital solutions. In this talk, we discuss why analog computing is uniquely well-suited for machine learning on the edge, due to low energy consumption, low latency, and high capability. We also explored several of the industrial applications that are using analog computing today, including machine vision, sensor fusion, and industrial drones. If you find these conversations valuable, please leave us a comment and a 5-star review. And if you'd like to share your company's story or recommend a speaker, you can email us at team@iot1.com. Finally, if you have an IoT research strategy or innovation initiative that you'd like to discuss, please email me directly at erik.walenza@iot1.com. Thank you. Dave, thanks so much for joining us on the podcast.
Thank you for having me.
Yeah, so Dave, I'm really looking forward to this one. This is a topic that is quite new to me, and I always feel like when I'm hosting this podcast, it's a little bit of my advanced studies, and it's kind of my continuous education in technology. And this is a topic I'm really looking forward to getting into. But before we do that, I'm interested actually in understanding how you came to set up the company. It's very ambitious, right? I mean, it's quite an interesting technology domain, and you basically set this up immediately after graduating. So if I see your CV, it's kind of like I did some internships, got my PhD, and then set up a company and raised $165 million. So successful, at least successful in the financing. I know success in business can be different from success in venture, but would love to understand what led you at that point in your life to feel like you could take on this very ambitious challenge.
Yeah, absolutely. We came out of the PhD program. Actually, I came out of University of Michigan, Ann Arbor, and Michigan has one of the best chip PhD programs. They worked with Intel, I believe in the 90s or early 2000s, to come up with what would be a really practical program. And so Michigan did a great job of preparing students for not just what is a piece of the chip design process, but also how do you do the whole thing end to end. And so doing the program there, I came out with experience building, I think, almost a dozen chips by the time I got done with the ones that I had led and the ones that my colleagues had done and I assisted on. And so my co-founder, Mike Henry, came out of Virginia Tech, and he and I had this idea of applying for SBIR projects, which is a government research program, and starting a company to develop new technology. And as coming out of the PhD program, you're used to working with faculty and they're kind of giving you the projects to work on. And this is our first chance at really pursuing technology that was directly in our interest and applying for the grants ourselves and pursuing it. And so we were able to win 2 contracts, one for analog compute for GPS signal acquisition and one for neural networks. And we were able to subcontract that to the university so that we were able to get a little bit of office space, some time from some master's students, and kind of work in the university environment as an incubator. Both of those projects did very well, and they both showed about 100x improvement in performance and energy efficiency. And we found that the neural network space is blowing up. We started in 2012. And so 2012 is when this foundational paper, AlexNet, had come out of the University of Toronto, I believe. And we were accelerating that algorithm. And in that time, the neural network space kind of really blew up. It went from something that was a curiosity in the 20-aughts and became a mainstream research space in the 2010s. And so since then, it's been quite the experience building a technology and a company around it.
Yeah. Okay. So good timing, but also it's a luxury, but it's also really a success factor of being able to do something that you're personally interested in, right? When you talk to founders that have a passion, they tend to stick with the problem and be much more successful.
Yeah, it's anytime you're building a company or doing a new technology from the ground up, you're always going to run into challenges. And so the more you're willing to push through, the more late nights that you're willing to spend and think about these hard problems and solve, the more likely it is that you're going to succeed. So definitely working on interesting, exciting technology has been helpful to us. But then also for recruiting and finding investors, I mean, people are excited about the technology that we're developing. And that makes a big impact in our success beyond just our own enthusiasm, but all the people that we surround ourselves with.
Yeah. Well, let's get into what you're actually working on. So give us the 101 first. What is analog computing and how does it differ from the more traditional computing approaches?
Yeah. Analog computing, when we think about digital is about ones and zeros. So if you want to represent a number like 125, you actually need at least 7 bits to represent that. And when we talk about bits, those are effectively digits that can be represented with only one or zero, so binary. If you want to go up to larger numbers like millions or billions, then you'll need more bits, so 20 bits, 30 bits. Physically, what that means is for each one of those bits, you have to have a separate wire. And those separate wires go to separate transistors, which are devices that can move the wires up or down. And anytime you're moving a wire up or down, you're going to expend energy. And so when we think about, hey, my processor is draws 100 watts or something like that, what the 100 watts is doing is it's moving a bunch of wires up and down. Every time you move a wire up or down, that uses up a little bit of energy. And so when we do analog computing, what that does is instead of having the wires representing one or zero, it could represent maybe 27 bits of information on a wire. So 27 would be 128 million different values. And so instead of having just 2 values, you could have 128 million values on that wire. And by compressing all the information into a small number of wires and a small number of transistors, you greatly reduce the number of wires that are moving. So now you've dramatically reduced the energy consumption, but you've also reduced the distance that information needs to travel. The speed of signaling on a on a wire is, I think, less than half the speed of light. And so that speed of light seems really fast. But when you go and you're operating at gigahertz speeds, it's actually measured in centimeters as opposed to like microns. So normally when we're moving signals across a chip, you're thinking about how many microns am I moving that? How much time is that going to take? And even at light speed, that's what slows you down. And that's why you can only operate at, say, 5 gigahertz instead of 5 terahertz. And so the information density that we're able to achieve with analog allows us to save energy, allows us to move faster, and that allows us to build basically smarter systems, more powerful systems, and more efficient systems. Now, the drawback is when you're using analog, it can be difficult to, if you have 128 million different values on a wire, it can be difficult to determine, what precise value is on that wire at any one time. And there's going to be a little bit of there's always noise in analog signals. So if you like turn up your speakers really loud in a stereo, you'll start to hear a little bit of crackling. So there's always what's called the noise floor. No matter what system you build, there's like going to be a tiny bit of noise in the end. And so you can't use analog computing to, say, run Excel or anything where you'd want to have a extremely precise value at the end, because as soon as it's analog, there's going to be some amount of stochasticity to it. But in neural networks and other signal processing applications, these require not precision, but very good estimations. So I think we'll get into that a little bit more. And all of the most difficult computing problems, or not, I shouldn't say all, but many of the most difficult computing problems of today are taking some sort of signal like a camera or a microphone and trying to figure out what was seen or what was said. Or even if you think about somebody takes some action in front of you, you're trying to interpret what they're doing. And that might be not just vision, it might be trying to figure out their body language, their intent. And so these problems don't have the same level of specific answer like an Excel spreadsheet would. It's a predictive problem. And so that's where this is a domain where we can really leverage the analog computing.
Okay, so that makes sense. So if you're doing a financial analysis, there is a correct and an incorrect answer, and you want to use digital computing so that you can have a structure that provides only the correct answer. If you're using analog, or if you're dealing with any kind of machine learning, you're dealing with a probabilistic answer, and therefore analog is fine because anyways you're going to get the data allows only a probabilistic answer, and analog can get you to that answer quicker, cheaper, with less energy, and then I guess a sufficiently high success rate that is the success rate for analog. Does that end up also suffering to some extent versus digital for machine learning, or are you able to match or exceed the accuracy also of projections?
We can definitely match or exceed. There's a couple different aspects of this. So one is how powerful was the neural network in the first place? So smaller ones tend to be a little more fragile, and they may not be able to have enough extra capacity to take on the analog nature. But most modern or almost every modern neural network will have sufficient capacity to work with analog computing. And in practice, what we see is if you're using a computing technology that allows orders of magnitude improvement in energy efficiency and performance, then you can apply a much bigger neural network to the problem. And so in practice today, our customers are typically not able to run the latest and greatest neural networks that are out there in research. So you'll see research papers with enormous networks that require like a multi-$1,000 GPU to run, and it won't be able to run real time. And it's certainly not on the hardware budgets that device makers are working with today. You can't put $1,000 GPU into a $250 consumer device, for instance. And so the question becomes, if I'm going to buy $10 worth of silicon and put it into this device, what is the biggest neural network I can put in there? There's been a whole class of research around that problem. There's networks like MobileNet and EfficientNet that are specifically targeting for these embedded systems. How do we fit a neural network that's at least moderately capable into that budget, both from there's a budget from a cost perspective, and then there's also the budget of just cooling a system. You can't draw 500 watts inside of the space of a small camera, for instance. And so what we allow them to do is upgrade from these really small neural networks that were designed for small embedded systems and upgrade them to more advanced neural networks. And that improvement in just the model that you're using provides a big increase in accuracy. Now, what we've also seen is for digital systems, many of the competing products out on the market, whether it's a specific accelerator or even like an NVIDIA GPU, there will be a lot of focus on model compression, is what it's called. So taking a neural network, it might have, say, 10 million weights in it, so neuron parameters. And they try to trim away, say, 90% of those or 99% of those in order to make the model smaller and more efficient to execute. And many times what we see is the amount of pruning that device makers are forced to do to try to fit these models inside of an embedded system ends up being a huge loss in accuracy, far beyond what the little bit that would occur from switching to analog signals.
Okay, interesting. So if it's let's say Google or somebody that wants to build a large LLM, they'll do this in a data center using maybe NVIDIA A100 chips because they can put the data center somewhere where energy is cheap and space is abundant, and and it's highly centralized. But if they then want to deploy an algorithm on anything that's embedded in a normal device, I guess, whether it's a computer or an IoT device of some kind, a car, anything like this, then that approach is not going to work, or they're going to have to trim down significantly to the point where the results start to suffer. If we then look at the device specifications in terms, so energy, you've already identified. If we look at the form factor, the size, if we look at the cost, how do those tend to compare? I mean, I guess you're comparing a bunch of variables, so it's not kind of a an apples to apples comparison, but what it tends to be the difference in terms of form factor and the difference in terms of cost structure for an analog versus a digital solution for, let's say, sophisticated IoT device.
Sure. Let me just add something about the difference in cost in terms of the applications. So I think I was reading an industry analysis report recently that said that the ChatGPT 4, which is one of the models is getting a lot of attention right now for the LLMs, to run that model required 2 large servers. Each cost more than $250,000. So like from a form factor perspective, it's like probably 16U tall, $500,000. And so the latest and greatest research that you can find and the things that grab the headlines are these enormously expensive systems. But when we think about trying to take that research and impact industry, many of these systems that we're working with are like a camera system or a small robot. It might be able to draw somewhere between 5 and 20 watts for the total power budget. The cost of the hardware, like the computing hardware, probably needs to be less than a couple $100. And I mean, this is pretty uniform around like the industrial space, for instance. I think we get a pretty consistent picture there. On the consumer side, it's even more restrictive because, consumers aren't typically, except for like Apple devices, they're not paying thousands of dollars for one system. So in terms of what implementing an analog compute accelerator versus a digital accelerator would look like, from the outside, it's actually very similar, the same. So our chip works as a PCI Express attached accelerator, meaning like kind of like how you'd have an NVIDIA GPU attached to a PC. In our systems, you'll have an SoC like an NXP platform, for instance, or a TI platform, and it'll have a PCI Express port, which will talk to our chip. Inside of our chip, there is analog computing engines, but the top level of the architecture is actually digital. And so it's not that the entire chip is analog, it's that there's certain key operations that map really well to the analog domain. And those are these matrix multiply operations. So you'll have, when you think about neurons, you have like your brain has, billions of neurons. In a neural network, they're in these what's called layers. So you'll have like maybe 64 neurons in one layer and a couple thousand neurons in another layer. In our analog compute engine, we can store 1,000 neurons, each that can take up to 1,000 signals from other neurons. And it can calculate in one shot 250,000 matrix multiply operations, actually should say multiply accumulate operations from matrix multiply in one shot. And that matrix multiply operation, that's done in the analog domain. But the signaling between these analog compute engines, the signaling between the neurons is digital. And so the way that we do that is on the input to the matrix multiply, we convert from the digital domain to the analog domain. Then we do this really powerful, complex operation in the analog domain. And then we take the result out by converting it back to digital. And so what that allows our system to do is we get the benefits of analog computing, the efficiency, the performance for doing those big matrix multiplies for the neurons. But we also get the benefits of digital communication, storage, and programmability. So we can map any neural network to the system because ultimately there's software that's managing each of these analog compute engines. And so from the point of view of the software, we're a grid of compute that just happens to have very high performance matrix multiply operations built into it.
Okay, got you. Okay, great. So the usability similar, the form factor and the cost structure is similar, but then the capability much, much higher for certain types of problems. Let's get into the types of problems that are a good fit here. So your team shared through via email a few cases. So drones, industrial automation, video security, smart home, AR, VR. So here we're talking about messy data. I guess that's kind of the theme here. So talking about video, images, audio, and then making predictions based on those. What for you defines a great use case? And maybe you can illustrate it with a couple, if you have to keep customer names proprietary, but if you want to illustrate it with a couple examples.
Yeah. So we're actually a general purpose signal processing system. So the other research project that we'd worked on in the early days was GPS signal acquisition. And that used a very similar technology. We could actually implement that in our analog compute today. And in that case, you're receiving these signals from a satellite that are below the noise floor, meaning that if you're looking at the signal coming in from the satellite, it just looks like noise. You can't actually see any signal at all. And that's recovered through these massive million term matrix multiply operations. You have to do a search to find that satellite signal by comparing different time steps with a pattern. And so any type of signal processing application can be a good fit. So some of the ones that we talked about today, or some of the ones that we talk about in neural networks, I should say, or, object detection or image classification, where you're looking at a picture, then you're trying to find, say, like people or objects, or you're trying to find defects in some sort of product. We can also do signal processing where we're maybe upscaling an image. So there's interest in the television space, for instance, where you start with maybe a very low quality, like a think about your cable box. There's a lower resolution signal, highly compressed because the channel has limited bandwidth it's sending. And you want to upscale that to your 8K TV. And so you can use neural networks to upscale your image in real time from that highly compressed, low quality, low resolution signal up to 8K, remove the compression artifacts, provide the higher resolution, and so on. There's opportunities in, say, like radar and sensor fusion. Again, looking for, like a LiDAR system, you might be looking for objects in 3D point clouds, or trying to figure out where walls or lanes are that for self-driving cars or automotive space. So I think today we're very focused on computer vision as a starting point. And we have our roots in signal processing and see a lot of opportunities in that space as well. In terms of what we're working on currently with customers, a lot of those customers are looking at more classical computer vision. So trying to, like, if you're in a factory, you'll have some product that you're sorting into maybe grades. And like if it's produce, you may be trying to sort, is this a really high quality apple or a lower quality apple? For instance, like this one is something that somebody would like pick up at a store and want to buy, versus this one might be better for applesauce. And these machines need to move extremely quickly. And you can easily calculate in terms of the processing speed. If I can process this instead of 10 milliseconds, it's 5 milliseconds. How much money does that save? If I can improve the accuracy from 90% to 95%, how much money does that save? And so the industrial space has a lot of opportunities for applying these technologies earlier. So consumers might not see them. They're kind of more affecting their supply chain than affecting the things that they're interacting with on a day-to-day. I think in terms of consumer applications, we've seen like the smart doorbells and security cameras, at least the ones that I've worked with at home, the ones I've had at my home. There's some attempt to put computer vision into those systems, but at this point, the processing capability that they've been able to implement, given that cost and form factor, has not been high enough to allow the really high accuracy neural networks. So that's something that we're hoping that we can change, so that when you get like a face detection at home, and I think my security camera recently told me that my brother was in my house and he's like in Minnesota right now and I'm in Texas. So it's like, okay, obviously he's not in my house. And so can we, make it so that these technologies are actually reliable? That's going to require an order of magnitude improvement in computing performance. And so I think that's something that these analog computing technologies can help rectify.
Mm. So it sounds like, just based on the examples that you've given, the industrial machine vision there, you might think of something like $10,000 per device, maybe with a subscription around that, and the manufacturer is happy to cover that cost because there's a strong business case behind it. If you talk about a consumer application, you're talking about maybe a few $100s per device. So you have to, or drones for that matter. I guess you have industrial drones where you could be talking about tens of thousands or hundreds of thousands of dollars, but then consumer, you're again in that hundreds of dollars of range. What is a time frame that you think is reasonable for getting from an industrial edge computing solution today down to a consumer device, or maybe I guess a lot of factories would rather just take an off-the-shelf camera and be able to work with this instead of paying for really a more sophisticated solution. So if you could also get to the point where you can embed it in a more or less an off-the-shelf device with a very affordable microcomputer, I'm sure you'd have a market in industrial as well. But what's the time frame for getting down to that cost level?
Yeah, I mean, we're working with industrial customers today, and I think our second gen is going to have a big leap in terms of cost and energy efficiency. And so the second gen that we're developing will be available in 2025, 2026. It takes another year or two to actually get to the market for, because it has to be built into those consumer devices. And so I'd expect to see that in 2026, 2027 timeframe in the consumer space. But for sure, the industrial space tends to be, from what I've seen, more focused on saving money, and usually it's about saving money somehow. And then the consumer space is more focused on convenience or novelty or entertainment, and so that tends to be a little squishier. It's what will people pay for as opposed to a straight formula. And so I think getting the cost down is very important there to help move the needle, and I expect that will happen in the next couple of years here.
Yeah, I mean, I guess one other important factor there is scale, right? So like the chips that are in our iPhones would cost a lot more if Apple wasn't selling 100 million of them a year, right? If they were selling 10,000, the price point wouldn't be where it is. If you look at analog, is it using the same basic manufacturing capabilities as the more mass market chips, or do you have to also kind of innovate and figure out how to scale the manufacturing technology?
No, we use standard manufacturing technologies. The only unique part is we use embedded flash, which is a little less common, but is still not a technology that we've created. It's something that's available at almost every foundry and a subset of processes. For sure, if we were selling as many chips as Apple, we'd be able to negotiate better pricing with our suppliers. So
Yeah.
that I hope that we'll get there eventually. But we're using standard technologies today, and that's one of the key advantages for us. The other thing is that because we have these advancements in energy density and performance, we're actually able to use older process technologies. So our first gen is in a 40 nanometer process, that was modern. I want to say like 2006. So that was a while back now at this point. But because we have these huge increases in energy efficiency and performance through the incredible information density, that allows us to use these more cost efficient processes like 40 nanometer. Our second gen is going to be in 28 nanometer. And so we kind of have a reset on Moore's law, which has been important because the newer process technologies today, I think I saw Apple was using like 3 nanometer. Those are insanely expensive. And for a startup to, or even a large company to try to do a new technology on would be very challenging just from a implementation cost point of view. And so we're very fortunate to be able to use and be very competitive given the process technology that we're in today.
Hmm. I noticed one topic that was not covered in your markets, which I thought was interesting, which is the automotive industry, because it feels like a lot of, I mean, if you're talking about machine vision, okay, maybe this is a bit more the future of the automotive industry as opposed to where it is today, but that seems like an important topic. And then kind of the low latency value proposition seems quite strong for this case, since there's kind of life and death issues regarding information processing there. How do you view automotive? Do you see that as an industry that has high potential, or do you see that as a bit still more like 5 to 10 year time frame before they're really investing heavily in kind of ML on the edge for vehicle operations?
It definitely feels like that space is increasing. The number of cameras on every vehicle is like doubling from generation to generation. And so we see that as a space we want to go after. And we have some compelling advantages, as you mentioned, the latency advantage, which we haven't talked about yet, and the just the cost advantage, being able to put AI computing every single camera and streaming back high level information as opposed to trying to stream back super high resolution video from every camera back to a central processing unit. That reduces the complexity of the system quite a bit, being able to spread out the compute across the cameras. And so we see a big advantage there. We haven't gone after that space yet. Just as a startup, anytime you go after automotive or medical, anything where there's safety critical aspects, it greatly increases your costs and your time to market. And so we're starting on the more standard industrial spaces and that can move quicker. And then once we've a firm footing there, then we'll move into the automotive space as well.
Yeah, got it. Well, yeah, let's touch a bit more on latency, because often when we talk about latency, we're talking about transceivers and kind of the data moving from, let's say, the sensor to cloud compute location or some edge computer location. But in this case, is it more the latency to perform the operation? Is that what we're talking about when we're talking about improvements here?
Yeah. So when we think about latency and machine learning, there's a question of, if I send an image to my accelerator, how long does that take for it to come back? And that's not opposition, but that's different than throughput, which is how many, say, images can I process per second? And the reason why it's different is because you can process multiple images in parallel. So you could process either in batches where you might be processing groups of 16 at a time, or you could be processing them in a pipeline where maybe you're processing 4 at a time and they're sequential, but it takes like 4 time slots worth of time to get through the system. And so when we look at digital systems processing neural networks, there's a big challenge where neural networks and other machine learning technologies have a huge number of weights that they need to work with. And so it might be, say, 10 million or 15 million weights to a neural network. And so digital systems typically, especially in the embedded space, typically can't store all of those weights on chip at the same time because the chip will be too small to have that much SRAM. You just don't have like tens of megabytes of SRAM typically on a small microchip. And so what they'll do is they'll load the first part of the neural network, process that, then load the second part, the second set of weights, process that part of the neural network, load the third set of weights, process the last third of the neural network, and then repeat for every frame. But since there's delays, every time you're loading a different section of the neural network, there's a delay getting the weights from DRAM or other storage, but typically DRAM. And so in order to amortize that cost, systems will often do this batch processing where they'll process, say, 16 images at a time. And so now you have a delay for loading the next section of the neural network, but that delay has been amortized across 16 inputs instead of one. And in neural networks, this is a big impact because running a section at a time, that's being done for every single frame. So if you're running, say, 30 frames per second to match the video speed, that means 30 times a second, we're loading the first section, the second section, the third section, first section, second. So those delays add up. So what analog computing does for us is We actually have, I mentioned that embedded flash technology from or earlier in the segment. And we're actually using this. So transistors are these storage devices. You actually have them in your phone now, or your SSD. So your SSD to your laptop, or the SD card in your phone. These devices are both use flash transistors. And a flash transistor is a special type of transistor that has a floating capacitor inside of it that can store charge. And so you'll store thousands of electrons inside of each of these transistors. And instead of storing just two levels, like one or zero, you can actually store multiple levels, because instead of storing, like, say, 2,000 electrons, you store 250 electrons, and that means some number. And this is called multi-level cell technology. So high density SSDs actually have this today. You can buy a hard drive on Amazon that uses multiple levels per cell. And what Mythic does is, instead of storing, say, 16 levels on one of these flash transistors, we'll store 128 levels on it. And that allows us to have not just 10 megabytes of weights on chip, but we actually have 80 million weights on chip. And so we're able to store the entire neural network on the chip at the same time, because we're able to store hundreds of levels on each flash transistor. And by doing that, we don't need to load sections of the neural network. We can run the entire neural network in one shot. We don't need to batch the processing, so we can run a single frame at a time. And so our latency going through the neural network is much faster than what you'll see in a digital system. So any sort of application like AR, VR, or systems where you've got moving parts like the sorting machines I mentioned earlier, or navigation, where latency ends up being very critical, this technology can make a huge difference.
Okay, great. Thanks for walking through that. So, yeah, very interesting. So it's a completely different way of storing data and then processing that allows this capability. Two more questions that I wanted to touch on, Dave. The first is how you work with customers. So, from a customer perspective, what does engineering with analog look like versus what they might be doing today? If somebody's building an IoT device and they say, hey, I want to explore this, I want to build up a prototype, what does it take to build up a prototype? And then if they say, I want to go and move this to production, what does that take? And how do you work with them? Do you basically just ship the chips and say, call us if you have questions? Or does it tend to be more of a deeper engagement through the development process?
Today, it's definitely a more hands-on engagement, just because we're in the early days of the company. And this, anytime you're developing new software, it tends to be a little rough around the edges. And so we work very closely with the customers that we have today to address the problems that they're running into. And that's not unusual for this space. What the long-term vision is that it will be the same as, say, doing what's called quantization aware training and compilation for digital systems. So anytime you're deploying a neural network onto a system, you need to analyze how efficiently is that neural network being executed on the system. Every system has limits in memory and compute. And so depending on how you develop the architecture of that network, it's going to impact the performance on that you see in silicon. And so researchers will do what's called a network architecture search, where they have a tool that will search for the most efficient neural network architecture given the hardware platform that you're targeting. We will plug into those tools just like any of the digital systems. And then for the analog computing, today we use what's called analog aware training. So you can take your neural network and you're training with a model of the analog effects, and that allows the neural network to adapt to those analog effects. Just like for you currently, when you're looking around your room, you don't see all the noise that your eyes have inherently in them, because your brain filters those out. But if you're really groggy in the morning or something, sometimes your vision will get a little static noise in it, because since you're tired, that filtering isn't as effective. And so analog training for neural networks is similar. The neural network can learn to ignore any analog stochasticity, and so we provide the tools to train, and then we're going to make it automatic, just like it is for quantization aware training.
Oh, interesting. Okay, yeah, that's a different topic, but I've been listening to a few podcasts lately on how the brain processes information, and it's really fascinating, quite counterintuitive, right? But different.
Definitely when I read about the brain and the signaling that it has, and it's pretty incredible compute technologies that we run on as people. And I believe the accuracy for human neurons is similar to the ones that we use at Mythic. So we operate with 8-bit precision. And if I remember right, the neurons in the human brain are around 7 bits. And so we're definitely able to do very capable or powerful algorithms with this type of technology. It's a matter of building the right software and systems around it.
Yeah, that's right. The more you kind of learn about how humans process information, the more you feel like, yeah, we could probably build a silicon computer that, basically operates as capably as the brain, at least in some areas, right? I mean, there's nothing magical about the brain. It's just a very sophisticated processing machine.
And we're in the early days of all this, our understanding of the brain's early days, the neural network research like ChatGPT and all that stuff, those are early days. And then analog computing that we're doing is also very, very early. It's we have our first generation today. And definitely the first time you take some technology to market, you learn like, oh, I made every single decision I made. I know how to do that one step better now. And so we're really excited about our second gen, and we have an exciting roadmap after that as well.
Yeah, well, that was going to be my last question, which is basically what's exciting to you about the future. And so you have a second gen coming. I don't know if there's anything else, but what would you like to share about the future of Mythic?
Yeah, so our first gen we have today, and we're able to, on the second gen, we're immediately able to do a order of magnitude leap in terms of energy efficiency and performance. And so that's why we're able to get into that consumer space and really bring powerful neural networks to consumer devices. So say running 4K video at 30 frames per second for your consumer camera system is not something that you could conceive of today. And after that, LLMs are making a big splash today in that server environment. We talked about the $500,000 pair of servers, huge amount of power, huge amount of material cost. What if we could take that and bring it down to something that's, say, like $1,000 that you could put into something the size of a toaster and run on, say, like 100 watts? That would be a big impact for businesses in the industrial space. I don't know if that's something that would impact the consumer space due to the cost, but maybe if Apple makes it, they could sell that. But I think that's where we want to head next, is trying to shrink the giant server down to something that you could conceivably put on your kitchen counter.
Yeah, I mean, even just getting this into a shipping crate that somebody can put on their corporate campus, because I talk to so many people in industrial about using LLMs and just putting data onto a cloud, even if it's Azure, for a lot of factories, it's just a no-go, right? And so they just want on-premise for a lot of these applications.
Yeah, you don't want your data being disseminated, but also you need to worry about uptime, right? Like if your internet connection goes down, you don't want your factory to stop. And so being able to have everything locally allows you greater reliability, better latency, and scalability. So I definitely see like LLMs moving to the edge. Cloud is great for new technologies and deploying it at scale, but ultimately real life happens at the edge. And so that's where we think we can make a big impact, is bringing those products to where they're used.
Awesome. Well, Dave, thanks so much for taking time to talk us through this today. I will definitely reach out to you in 2 years, and would love to have an update once you're launching the next iteration. But really appreciate it. Thank you.
For sure. Glad to be here. Thanks for having me.
Thanks for tuning in to another edition of the Industrial IoT Spotlight. Don't forget to follow us on Twitter at IoT1HQ and to check out our database of case studies on IoT1.com. If you have unique insight or a project deployment story to share, we'd love to feature you on a future edition. Write us at eric.walenza@iot1.com.